So now that we've kind of talked about, in a very general, very broad sense, what it means to think about the behavior of a function in a neighborhood around a point, but not necessarily at that point, we know enough about this now that we can start making this more precise, that we can come up with a real mathematical definition of this concept. So before we do that, I want to stop for just a minute and talk about absolute value. Now, I'm sure you know what absolute value is. I'm sure you know in a mechanical sense how to calculate absolute values. But for our purposes, I need you to remember there's another way to interpret this, right? The absolute value can be seen as the distance between 2 points in one dimension. So the absolute value of 3 minus 1, it doesn't just mean 2, right? You can interpret this as the distance between 1 and 3. And of course, it's an algebra calculus thing. If we can do it with numbers, we can do it with letters. And so this would be the distance between x and 3. And we can put inequalities in this, or equations. We're going to be interested in inequalities. So what this is saying, right, working my way down here, this is saying the distance between, oh, that got messy, sorry. The distance between x and 3 is less than 1. Right, and this last version here, this is the one that we're actually going to see in our definition, right? Because you remember when we were talking about our kind of generic examples in the last lecture, we didn't want to let x actually ever equal c, right? So this last one here, this last inequality, is saying the distance between x and 3 is between 0 and 1. Right? That's the version of this that we're going to use in our formal definition. Right, so let's look at an example here. Right, this is our informal definition. This is where we ended up on the last lecture. You remember it had some kind of inherent imprecision. What does it mean to be close? Right? How can we quantify that? Well, that's what we want to do here. And because close, right, is an observation about distance, that's where that absolute value is going to come into this. All right, so here's our formal definition. And I know it's one of these math things. It's big, it's wordy. And I want you to take a minute, right? Take a minute, read through it. I'm going to stop talking for a second. You can pause this if you need to. See if you can kind of think through at least parts of it. Right, then we'll come back and discuss it together. Okay, so let's read through this. First, we say that the limit of f of x as x approaches c is the number L. There really isn't a lot of math in there yet. Right? Really, that's kind of the English part of the definition. That's telling you how we're going to say this. How we're going to read this if you see it in a problem or in a textbook. It's the next part that actually does the math, right? For every epsilon greater than 0, these epsilons, they're going to be small, right? Because we want to talk about close to. We want to talk about small distances. So for every epsilon greater than 0, there exists a corresponding delta greater than 0. So we know these two are going to be tied together somehow, such that these things are true. The absolute value of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. Now, okay, that absolute value, that's distance, right? So what this is saying is f of x is close to L. That's the technical way of saying it. Right? That's the mathematical way that we're going to say close to. And you've got the same thing down here. Right? This is saying X is close to C, but X is not equal to C. That's this part here at the end. The only way the absolute value of X minus C it could be equal to 0 is if X is equal to C. So that little part there at the end, that's ruling out that possibility. Okay, so in practice, what I really want you to keep in mind is this part is the driving part. Okay, if you can pick an interval around L, doesn't matter how small an interval you pick, for L to be the limit, I have to be able to find a corresponding interval around X so that every number in that interval, every number in my X interval, gets mapped into your f of X interval. All right. One more thing, but before, obviously we're going to look at some examples, right? But before we move on, let me get the notation in here. The way we write this is the limit LIM as X approaches C of f of X equals L. Right? That's the actual written notation that we're going to use. When you excuse me, when you see that, what you should think is this right here, right? Because that's how we read it. That's all that first part of the definition is saying. All right, so how about some examples? Look at this thing. Starting out with something very simple, just a line, right? And what I'm saying is I'm claiming that the limit as x approaches 2 of 2x minus 1 is 3. Okay, so first, let me pick out some pieces here so we can equate this back to the definition. Hopefully you wrote it down. F of x is 2x minus 1. L, that's the actual limit, that's 3. And C is the point, the number that x is approaching, that's 2. Okay, so let's go over to the diagram now. All right, x equals 2 is here. Y equals 3 is up here. So what this definition is saying, okay, is if you pick an interval around 3, right, you can make it as small as you want, doesn't matter, all right? This distance here, the distance from 3 to each endpoint, that's epsilon, right? Let me just flash back to the definition real quick. Oh, I can't go back to the definition. Sorry. So we'll just stay here. That's the epsilon. Okay, and what this is saying is I have to come up with an interval around 2 so that every point in here gets mapped into here, right? So the epsilons are up there, and the distance from 2 on either side is going to be delta. Okay, so here's how I'm going to do this, right? Here's how I'm going to do this. I'm going to go to the definition. The definition says the absolute value of f of x minus L is less than epsilon. Okay, so let's put these things in here. Let's put 2x minus 1 in here for x, and I'm going to put 3 in here for L. I literally just took these two numbers, one number and a function, substituted them into the formula, into that little inequality. All right, so now let me play with this for a minute. This is the absolute value of 2x minus 4 is less than epsilon. Right, but now look at what I can do. I can factor a 2 out of there, right? This is the absolute value of 2 times x minus 4. And I can separate those. This is the absolute value of 2 times the absolute value of x minus 4. With the absolute value of 2, oh, whoop, I didn't factor, did I? Sorry, that should be a 2 there. The absolute value of 2, though, that's just 2, right? So this is just 2. Now look, let's do this. Divide both sides by 2, right? And see what I get. I get absolute value of x minus 2 is less than epsilon over 2. That is my delta, because notice that that is equal to c. Okay, everything I did here, you can work it backwards, right? If x minus 2 is less than epsilon over 2, then this is true, and this is true, and you can keep working your way back up here until you get all the way back to the absolute value of x minus L is less than epsilon. Okay, that's what I needed to show. I found the epsilon that corresponds to delta, and what is it exactly, right? I'm saying epsilon over 2 is delta, which means no, yeah, sorry. So, and that's where we stop. Delta is epsilon divided by 2. Okay, so again, just to be clear, right? Looking at my diagram, if I pick any number between 2 plus your epsilon divided by 2 and 2 minus your epsilon divided by 2, every number in there, no matter how small you pick epsilon to be, every number in there is going to map into this interval up here. Okay, so let me bring another one up here, right? Take a look at that one, right? See, it's also a line, right? It's going to be very similar. See if you can't walk through that one and show that this is true. Remember, what you're trying to do, you're trying to find a delta that corresponds to epsilon. You can go ahead and pause, right? Start this back up, and then you can see how I do it. Okay, so we're gonna approach this exactly the same way. First, just so we're all on the same page, let's pick out some parts. F of x is 4 minus 5x. L is negative 1. And C is positive 1. Okay, so what do I want to do? I'm going to start with f of x minus L is less than epsilon. And my goal is to get to start working, right? And in the end, I'm going to get the absolute value of x minus 1, that's my C, is less than something with epsilons in it. And whatever that something is, that's going to be my delta. Okay, so let's see if we can do this, right? I'm going to put 4 minus 5x in here for x, in here for f of x. And I'm going to do, careful now, this is going to be minus 1 less than epsilon. And, okay, so let's see. Minus 1, that's plus 1. Add that to the 4. This becomes the absolute value of 5 minus 5x is less than epsilon. Okay, now look, I could take a 5. It's kind of the obvious thing to do, right? Take a 5 out. But I'm looking ahead. I want the x to be in front, right? I want it to be x minus something, not something minus x. So let's do this. Let's take a minus 5 out. Right? If I do that, this becomes the absolute value of minus 5 times 1 minus x, times minus 1 plus x less than epsilon. Now let's split them up. Absolute value of minus 5, absolute value, and I can flip these, right? make this x minus 1 is less than epsilon. And the absolute value of 5, that's just 5. So this is 5 absolute value x minus 1 less than epsilon. And look, see where we're about to end up, right? Divide both sides by 5. The absolute value of x minus 1 is less than epsilon over 5. And that epsilon over 5 is my delta. Okay, so what do we see here now, right? What we're seeing is every number between 1 plus epsilon over 5 and 1 minus epsilon over 5 gets mapped into minus 1 plus delta and minus 1 minus delta. Okay, now that actually, okay, this is true, right? But remember our definition was a little more specific, right? It actually said this, right? We didn't want to include 1. And actually, I'm okay with that, because if every number in here gets mapped onto that interval, then every number in here does as well. So actually, I'm okay. But let's look at another example here. This is the same one we did at the beginning, right? It's 2x minus 1. But I'm going to tweak it just a little bit. All right, I'm going to carve a hole. I'm going to go over here to x equals 2, right? And that's all the way up here. And what I'm going to do is, this is a little tricky. I got to get 2 colors going at once. What I have to do is I'm going to carve out this point here, right? And I'm going to replace it with something way out in, excuse me, it's not 5, it's 3. We're going to go up here to 3 and carve this point out. And I'm going to, this is where the 5 comes in. And I'm going to replace it with 5. So my function actually looks like this. And what I'm saying is, despite the fact that we have that wonky spot that I just pulled up into space there, the limit is still 3. Right? The limit hasn't changed. Right? And here's why. It's because of that 0 part. Right? I need the absolute value of x minus 2 to be less than delta, right? But you got to have that 0 less than part. In other words, I need every number that is closer, that is within delta of 2 to go into that corresponding epsilon interval except 2 itself, right? Because x equals 2 is the only number that makes that 0. And that one number doesn't have to follow the rule, right? So you see that this goes back to our concept of close to. What I'm interested in is what the function is doing at numbers close to 2. What actually happens at 2 if it wants to be undefined there, if it wants to blow up and go to some bizarre random point, I don't care. All I care about what the function is doing near that x value. Okay. So, where are we going now? We're going to do some more examples, right? We're going to do some nonlinear ones, some functions other than lines. Lines are pretty easy to do, right? Lines are pretty straightforward. We're going to take a look at a few more, right? Just to get some more practice with this and kind of see how it can be used even with functions that aren't as straightforward as the linear one.